Okay, so now we want to make the equation of the line, right? So what you notice is there's a little hat on here, right? Because it's not the exact line. So we used y equals a plus bx in the very beginning of this lesson because those were algebra and they were perfect and they've given you the exact answer, right? But this is an approximation, right? So it's y hat. What you'll notice is they'll either use y hat in modern textbooks and then y exclamation in older textbooks. And I'm going to use this in Excel because I can't type this in Excel. So I will use the old format on occasion because of the fact I can't type the hat when I'm in Excel. Which is what you should do too. You should never use just y for an estimation. That's not true. So this is the way you calculated the a and the b in Stats 1, right? So this is Stats 1, right? And this is Stats 2, the way we want you to do it, which is the quicker way to do it. Okay? So you can still use the sums like we did in Stats 1, but it's a little bit longer to do it. So we're going to do the Stats 2 method, which is using the standard deviations and the means, basically. Okay? All right. So, and of course, your A and the B are the same A and the B from the first section of the videos, which is the slope and the y-intercept, right? So the point is, there are an infinite number of lines you can draw through the data, right? So I can draw as many lines as I want through the data. But who's to say what the best line is? What it really comes down to is the residuals, right? The residuals is the distance from the predicted value, which is the line, and the observed value, which is the actual value from our x and y table. So those residuals are either positive or they're negative. So again, you take the predicted value and the observed value, and you do observed minus predicted, and you're going to get a positive or negative value. So this is a negative residual. This will be a positive residual, right? So they typically use it's not an E, but it looks like an E. It's a Greek letter. We'll go through that later on. But basically, you want to max and min all of these, right? Which is called a least squared method. And once you found the line with the best least squared, you found the best possible line of all the infinite number of lines you could have drawn, basically. Okay. So in short, you used this in high school, right? But that's when they were perfect lines, and that's American textbooks. This is what we use in stats because it's an estimation, because there's points all over here, you know what I'm saying? So it's an estimation, and we use a plus bx as far as the format goes. Okay, and you'll see a lot of different verbiage. It's the process of regression, so we call it the regression line, or the line of best fit. Is what they say in like high school, you know what I'm saying? Or the least squared line is what we're calculating, basically, because it's a process of squares. But we don't need to go through that until graduate level stats. But okay. So we're basically min-maxing the residuals as a long-term thing. So the points of the scatter plot must fit the regression line reasonably well, right? The R must be significant. And you can't use it in an extrapolation. Basically, if my data, just looks at kids who get, you can't look beyond the data set, basically. So let's say I do data on people who their healthcare costs in their 20s and their 30s, right? So I make a scatter plot of all the healthcare costs of people in their 20s and their 30s. But then I use that data to make a model, right? A linear model. Assuming it was linear, it's probably not. And I estimate the healthcare costs of somebody in their 90s. That doesn't make any sense. That's outside the data set. That's extrapolation. Or if I try to extrapolate a 2-year-old's healthcare costs, that doesn't make any sense either, because all my data was 20 and 30-year-olds. But now all of a sudden I'm trying to use that model to predict 90-year-olds and 2-year-olds. That's extrapolation, because I'm going outside my actual data set. Okay. So for the 3 data sets we have in this section, I want to find the linear regression line, right? And then explain what that the correlation coefficient is telling me about that linear regression line, basically. Okay, so we're going to go back here. What we need... Right, so I'm going to take this let's go to the spreadsheet first, actually. So we need to go to the spreadsheet. Where the hell is it? Right there. Okay, so I'm going to go to the car revenue, and I'm going to do the standard deviation of x, the standard deviation of y, how do I want to do the mean of x? Da, 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 da. Mean of x, I guess. I don't know. That sounds good. The mean of x. Yeah, why not? The mean of y. Okay. And we need, let's see here, let's shift those to the right. I think that's all we need for now, right? So let's get the little thingies now. Oh, A and B. A, no, I'm sorry, B, then A. You're like, well, A comes before B in the alphabet, yes, but you need B to calculate A. So if you don't remember why, let's copy these, right? So copy, paste, there's the B, right? Put that right there, and then we'll take the A, copy, paste. So you notice the formula for A requires the B using the shortcut method for stats2. Okay, so I'm going to copy each of these to the other ones. Get that out of the way. Okay. Alright, so standard deviation, and there's a population and a sample. We want the sample one, basically, of the x's. Standard deviation, equals standard deviation dot sample of the y's. And you want to average, what did it, I don't know why I did that. The x's, right? Or the average of the y's. Oh, there we go. Right? You can also do the sum of the values, right? And divide by, what is that, 6? 6 of them. Get the same answer, but that just does it a little bit quicker for you. Okay. So we got that. So now we want to do the b value, which is the r times the standard deviation of y divided by the standard deviation of x. Right? So that's using that formula right there. And then the a is the y mean, sample mean, right? That's why it's bar, right? B times x, right? So there's my A and my B. All right, we're going to pause there. We'll go to the next ones. So we'll copy, paste, paste, copy, paste, paste. Okay, let's go through and fill these things out. All right, so standard deviation sample, right? Because obviously this is not every single grade in the whole world, right? Standard deviation sample, average, 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 come on. Fingers are chunky today. Average, y. Okay, now I get my b value, which is the correlation coefficient times the standard deviation of y divided by the standard deviation of x. And then the a value is the y mean minus b times the x mean. You do see variations where they switch this. They put x mean then the b second. You will see that, but it doesn't matter. It's the same value either way. Okay, so we got that there. All right, so last one equals the standard deviation of x, standard deviation of y, and the mean of x, and the mean of y, and then r times standard deviation of y divided by standard deviation of x, and then y mean minus b times x mean. Okay, so there is those. So what's our equation basically? So our equation, right, is y hat equals, I don't know, we'll say 11.79, you know, 9 dot 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 plus 0.105 dot 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 times x. That's the equation, right? So our equation here, or our model regression line for this one, right, is y hat equals 102.49 dot 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 minus 3.62 dot 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 times x, right? And again, we're not going to round these. We're going to use the exact values when we estimate things later on, right? Okay, and this one, car revenue is y hat equals 0.396 dot 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 plus 0.106 times x, right? Okay, so let's verify we actually got those correct. So what I want to do is I'm going to click on my scatter plot here in the online version. And I believe if I go to chart and then format, right? I'm going to click on chart and then format. If I go down to the series and I go down to the trend line, right there, trend line 1 linear. I'm going to make sure it's on linear because there are other options, you know what I'm saying, which we'll do later on, but right now we just want linear. Equation and values, I believe is what we want. Okay, so if I notice, this matches up, right? But we don't want to round it off because we want the exact value for estimations later on. Okay, so we got that one, right? So we go to this one here, go to the graph. Let's zoom out a little bit here. I don't know why we're so zoomed in. I'll click on the graph, click chart, click format, and series, trend line linear, and then show the equation. Okay, where's my equation? So we got this one right here. Oh, I dragged it way too quick. No, stop doing that. It's being jumpy because it's the online version. Okay, does that match up? Yes, it does. Okay, so we're 2 for 2. Let's see, go 3 for 3 now. Click that, click chart, click format, series, the one we have on which is linear, and click on the equation. Okay, so now, does that match up if I can get it out of there? I think it does. The problem is these round, that's the problem, and that's not what we want. Ow, stop jumping. Okay, so we're good there. Okay, so we're right here. So add the regression line to the scatter plot. What does the correlation coefficient tell you about the regression line, right? And the linear equation. Okay, so what this is saying basically, when you answer this question, you can type that out or write it for yourself. For the first one, right, what essentially this R squared R is telling me, the correlation coefficient is, this is a good equation to make estimates. Because it's almost 1, so therefore this equation is going to make good estimates for the revenue, right? So if I input cars, I'm going to get a good estimate for revenue. What this is saying is, since it's almost 1 again, not quite as good as the previous one, but negative, it just says the direction it's going down, which makes sense. This equation is going down. This equation is going to make good estimates for final grades. So if you give me absences, I can give you a good estimate for final grades. Okay. What this is saying here is, this is not good, right? So we have an equation, but it's not good, right? That's not good. That's less than half, right? 0.44. So it's saying if you give me the number of teachers, I can give you a poor estimate for the student-teacher ratio. I can give you an estimate, but it's not going to be very good. That's what it's telling me basically. So we have a model, linear model, right? Regression line, which is the physical line itself, but only 2 of them are very good, 1 of them is not very good based on what we have. Okay? All right. Next video we'll do the residuals.